Setting up stream. Uh, I'm getting like chat and a second device for once, so I can like react better. Uh, um, Maybe I will give up. I'm trying to do it online, but maybe you can't comment online, like on mobile. I don't know. Who knows? Someone knows. Someone has to know. Uh, we'll figure it out. We'll figure it out at some point. Not today, I guess. Okay, we started coordinates yesterday. We didn't really get too far. Okay, we kind of yeah, we did some distance. I'll just recap, I guess. Uh, hmm, any three independent variables can form a coordinate system if they uniquely specify a point. Is convenient to start rectangular because we know it. And for transformation between the two, for it to be well defined and unique, you should be able to go back and forward. It is necessary that the inverse relations exist as well, um, as opposed to only having one relation from this to this and not from blah blah blah. And all these relations are single valued functions. For example, if we defined in terms of rectangular coordinates. Okay, so and all to be well defined is necessary that they exist, the inverse exists, and that the relation's single valued. So you shouldn't be getting double values. But I'm seeing here that theta is arctan, and like I know there's multiple values, but maybe the values loop around, right? So it end up being the same value, maybe. Okay, a coordinate axis now becomes a coordinate curve. Um, Maybe defined in terms of rectangular. A coordinate axis now becomes a coordinate curve, along which only one of the coordinates is changing. The coordinate curves in spherical coordinates are radius, along which only one of the coordinates is changing. It's easy to find algebraic expressions describing the coordinate curves because, by definition, only one of the coordinate changes along such a curve, while all the others remain unchanged. For example, this in spherical coordinates, and the partial derivatives this describe the vectorial changes along this. Okay, yeah. So I see myself like understanding this even more than yesterday already. Um, like coordinate curves, um, partials is just a change in one thing, right? So coordinate curve is just change in one thing, like in one direction. So for the three coordinate curves, you just like partially differentiate it in the direction of that curve, of the unit vector, I guess. The unit vector, I don't. You partially differentiate it in the direction of the coordinate, like these things, these guys. Okay. And all these describe the vectorial change along the coordinate curves. Each of these derivatives is a vector in space, yeah. And each of them have a length and direction, yeah. Uh, the explicit forms can be obtained readily Top of rectangular, yeah. Hmm. Ex explicit forms. What do they mean by explicit? Explicit form. Unstable. Explicit meaning. Stated clearly and in detail, leaving no room for confusion and doubt, yet I am a little confused. Hmm. Okay. The explicit forms can be obtained readily with the help of rectangular coordinates. Or, yeah, uh, del R R equal del R of this equal this. Yeah. Um, simple calculation then yields the magnitude of these guys, and when you to get the dr, you just add up all these together. You combine them after you split them up, and you get dr er. Yeah. For arbitrary generalized coordinates u1, u2, u3, coordinate curves can be determined in similar way by examining the displacement of each. The displacement, yeah. Each partial derivative is a vector, yeah. The tangent vector, nothing bigger, with a length and direction. The length is h, the direction is ei. Del, del r, ex, ey plus vj, del x, del ui. Yeah. In terms of these quantities, the original space one may be written in the form the sum of from I to I equal r theta and phi. Ei of r, yeah. dsi, where dsi is the magnitude of the magnitude of the partial, the, yeah, the magnitude of the partial multiplied by dui from the original expression here. Okay, and it's called the infinitesimal scalar displacement. What do you call a curve? The function HIR is called a scale factor and ensures that the displacement has the dimension of a length, irrespective of the nature and dimension of UI itself. You can get other geometrical quantities readily in terms of these guys. Thus, the infinitesimal scale is based on ds. Right, and then they just proceed to do it. Do they? Metric coefficients are generalized. The differential elements of surface and volume can be written down with the help of yeah. We found that. Yeah, I agreed with this. I agreed with this. The differential area element. The differential area element is just the cross of the two, um, like the plane that is. Hmm, well, for normal differential elements, well, this one is normal too, but for normal differential elements, it points in the direction that is normal to the plane of the um, displacements the plane is part of. So yeah, it makes sense. Yeah. And then yeah, all this makes sense. The differential volume is just I can't remember if this is a BS0, but it's kind of similar. Where if you dot product a like cross product, it'll end up being like a determinant. And we saw that to be true because they mentioned the Jacobian and um it's a 3D Jacobian. And there's also the 1D change of variable, which you could also use the Jacobian for. Okay. And now we move on to new stuff. Maybe I should drink water. Yeah, I'll drink water. Okay. Orthogonal curvilinear coordinates. I think this just means perpendicular, but in three ways. I think that's what orthogonal means. Let me Google just to make sure. Orthogonal meaning of or involving right angles. Okay. Uh, let's go back. If at every point R, the three unit tangents, I think they mean tangents. If at every point R, the three unit tangents EI of R are orthogonal to one another. Yeah. That is if the dot product is equal Kronecker delta. I forget what Kronecker delta is. If it's the same as zero, or... let me Google that real quick. Kronecker delta um, function. Oh, it is 1 if I is equal to j. Well, let me write that down. Okay. Kronecker delta I j, put a bracket there. 1 if I equal j, 0 if no, if not. That's it, right? Yeah. Okay. If at every point R, the three unit tangents are orthogonal to one another, that is, if the dot product like acts as a Kronecker delta, or even if del R del UI. Yeah, this is just. Is this just for with magnitude? Let me check. Um, hmm. HIR del R del UI. I think so. Just add the magnitude and it becomes del R del UI. Yeah. Multiplied by HI multiplied by HJ. Or equivalently, if this is proportional to this, so there's like a constant there. Well, and the constant would be HI HJ, right? Or maybe even no. Oh, okay. That is if this equals this or this equals this, then the generalized coordinates UI are said to form an orthogonal curvilinear coordinate system. OCC, orthogonal curvilinear coordinate system. In the system, the unit tangents form a Cartesian coordinate system, yeah, at every point R. The only complication is that their orientations change from point to point in space. Okay. Like a normal Cartesian coordinates over here. E, Z is always up, well, Y is always up, Z is always here, X is always here. You go over here, Y is up, Z is here, X is here. But for other coordinate systems, like maybe sphere, um, theta is R is so, but over here, R is so. So they're kind of changing from point to point. Um, at every point, the other combination that there, yeah. In an orthogonal curvilinear coordinate system, the metric coefficients, blah, metric coefficients this. I think this is multiple stuff in here. Where hi squared. Yeah, this is just like Pythagoras. The metric coefficients are diagonal. And the squared length ds squared. I need to write ds over here because I think it's simple, but I just forget it, okay? dsi equal hi of r dui. And while I'm here, I guess I'll write this. Let me change color. It's kind of a hassle to change color. I'm sure there's a better way. Color. Boom. Shoot. Del R. Oh my god, there's an image here. Del R. Del UI equal hi of R. ei of R. Okay. In an OCC system, the metric coefficients of this are diagonal. I don't know what that means yet. And the squared length does. Okay. Yeah, I see. The squared length does equal, yeah, to the stuff squared from I equal 1 to 3. Squared length. Summation of I. Oh, so ds and dsi are different. The difference being that ds is like all of them combined. ds is the sum of the dsi's, basically, is what they're saying here. In a nosy system, the metric coefficients bling are diagonal, and the squared length does not contain cross terms. The quantity dsi always has the dimension of length. The differential elements of surface and volume. It's also simplified to dsi dsj epsilon ij kek. Let's go back up here. dsi dsj dsi dsj. Then we have the cross. And nothing has changed at all here. Okay. And the tau equal ds1, ds2, ds3, where yeah, that makes sense, because yesterday I was a little confused because I computed this and ended up just finding 1. So yeah, this makes sense as well. But maybe in other scenarios, no, maybe. I was going to say maybe in other scenarios this does not end up being 1, but early in the book they defined EI to be unit vector, so it has length 1. So I don't see that being the case. Okay. Um, a diagonal. Thus, the DSI are very much like their. Hmm, hmm. I'm considering, do I Google something? Do I? Yeah, I will Google it, I guess. What? What does it mean to say metric coefficients diagonal? Okay, this is tensor stuff. Um, it tells you how to compute distances and angles. A diagonal metric means that the off-diagonal components of the tensor are zero. The off-diagonal. Okay, so you have a matrix C, and the stuff that is not in the diagonal, that means zero. Okay, this is how I read this. There's a matrix, and the stuff that is not in the diagonal is zero. Good to know, I guess. Okay, thus the DSI are very much like the rectangular coordinate DXI. Yeah, because the, the tau is dx, dy, dz. However, the tangent directions EIR do change from point to point, except in the special case of rectangular coordinates, for which they are constraint vectors. Do change. For spherical coordinates, blah blah blah. With the tangent vectors show that ER dot EI equals 0. Yeah, yeah. Okay. And ER cross E, yeah, if you cross two of the unit vectors and spherical coordinates, you get the third one, yeah. These orthogon these orthogonality properties are easily visualized geometrically because ER points radially outward from the origin. E theta points south along a longitude. South along the longitude. While E5 points east along a latitude. Also with DSR equal DR. Okay, well, what's DS? DS is the length of the thing, multiplied by DY. Yeah, so DSR is bling. Yeah, I agree with this. We find ds squared equal ds squared equal dr squared plus r d theta squared plus r sine theta d phi squared. Hmm. Hmm. Earlier we said ds equal like the sum of these guys here. ds. Did does this say this? ds squared. Can you pull this guy outside of the square? Sum of dsi squared. Bling bling bling. Squared. A plus b plus c. A plus b plus c. Hmm. I think I think the summation being inside makes it different because at the end of the day, you'll get a plus b plus c squared, which there's a lot of like, you end up with like a whole set of ab's and bc's and stuff. Like, at the same time, um, the way del works and partials work, it makes me think that this stuff doesn't matter. Like, that's just part of the notation. So we're seeing the same thing at ds squared. Even though ds is a plus b plus c, you don't get the cross terms. You don't get dr r d theta. I guess that's just how it is. That's just how they do it. Okay, ds squared equal this. We can live with that under these assumptions. ds squared equal this. I still don't know the symbol. I think it's sigma. Differential area element r theta. So it should point in the phi direction since this is the plane this stuff is on. Equals rdr. Yeah, you're just multiplying the the magnitudes, which is dr and rd theta to get rd theta. Yeah, I agree with this. And these should be no different. And they have this like third thing here. So if you switch around the theta and the r, it becomes negative, which makes sense because a cross b equal negative b cross a. And for volume element, you just multiply all these you just multiply all these guys. And secretly there's like ei dot, well, er dot e theta cross e phi, but that just computes to being 1, so you can just ignore this. So we end up with this. R squared sine theta, and then you add up all these guys, yeah. We can also define coordinate surfaces on which one of the coordinates is constant, while the remaining two coordinates change. Okay, like equipotential surface where one thing is constant. No, where well, in this case, two things are constant. The coordinate surfaces for spherical coordinates on which one of the coordinates. Yeah, one is constant. Yeah. So it is like equipotential surface. Um, the coordinate surfaces for spherical coordinates are spherical surfaces. Yeah, for constant r. Yeah, I can visualize that. Conical surfaces of constant theta and half planes of constant phi. I'll have to draw that in a bit to visualize it. For OCC systems, coordinate surfaces are perpendicular to coordinate curves. Coordinate surfaces are perpendicular to coordinate curves. Along which the third coordinate changes value. Coordinate surfaces are perpendicular to coordinate curves, along which the third coordinate changes value. One of the coordinates is constant. Okay, I'll have to unpack this sentence in a bit. For example, spherical surfaces of constant r. Um, So you have like a shell, perpendicular to the coordinate curve ER equal ER. Yeah, I suppose. Yeah, yeah, yeah. We list in table 1.1. I think this is table up here. The definitions of UI and their scale factors in two common OCC systems. The coordinate surfaces for cylindrical coordinates are the cylindrical surfaces of constant P, rho. Is this rho? Of constant P. The planes of constant Z and the half planes of constant phi. Um, more, yeah. Let me see if I should continue reading. Finally, we should know that the coordinate RT. Okay, this is another wormhole. Okay, let's try to visualize these coordinate surfaces. So the constant R1 is easy to imagine for me. Like, let's say R is 5. If radius is 5, um, if radius is 5 and you can move, like, maybe a marker will be good for once. Do I have a marker? You. Um, highlight. Ah, do I have a marker? Okay, we won't do a marker. Will we? Opacity. You can change stuff to markers with opacity. Okay. All right. So if R is constant, like this is the origin. Let's just have one of our points be here, and theta isn't constant, so we can move around all around. We can move our thetas around. So now we have this, and phi isn't constant, so we can also move in this direction. Well, we can do it for this section as well, and this section as well, and this section, and this section, and this section. And boom, you end up with a shell. So this is, maybe I should do it over here. I'll do it here, where I'm already doing it. Okay, next up we have, okay, this is kind of small. Uh, Next up we have, okay, let's do constant, like theta. Constant theta. Which one is theta and which one is phi again? Phi. I know phi is the one with this guy in it, r sine theta. And I believe that's like a cross like this. So theta is up and down. Okay, I could be wrong, but like the the diagrams for them will just be interchangeable then. Like if I make the change from type, if I make the change phi theta to theta phi. Okay, let's say theta is constant, so we can't move in this direction anymore. We can't move in this direction anymore, but we can increase the radius. So that's the thing we can do. Our point is here. We can increase the radius. We can decrease the. No, 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 no. The radius can't be negative. So we can only go in one direction with the radius. So this is what we have so far. Um, this is the limits of our radius. And now let's apply phi. Um, so for each phi, so for this point here, we can go around. Whoa, we can go around. And we can go around here, we could go around here, we could go around here, we could go around here. And after all this, you'll see we have like a plane. A kind of circle plane, but maybe not circle because it's infinite. It, hmm, there's some arguments there. At the end of the day, it is just a plane. This is easier to visualize than I expected, than I anticipated. Okay, next is constant phi. Let's start off with radius. We have a point here. We can decrease the radius. We can increase the radius outwards like this. And now from here we could go up and down. Like we can do this. And from here we can do this. We could do this, we could do this. We could do this, we could do this, we could do this, we could do this. I think that's how it is, right? Let's check our work. Hmm. The coordinate surfaces for spherical coordinates are spherical surfaces of constant r. Yeah, we got that. Um, Conical surfaces of constant theta. Conical surfaces. What is a conical surface? When I think cone, I think of this. Oh, hmm, hmm. Yeah, maybe I made a mistake. Maybe. And half planes of constant phi. Half planes of constant phi. So we got the half plane, yeah. We got the spherical shell, but we didn't get the cone, unless this is the cone. Hmm. So our radius increases. This guy goes around. This guy goes around. This guy goes around. We can't go up. Hmm. Shouldn't it also be a plane? Like this guy's a half plane. This guy's a plane. This guy's a sphere. Is a conical surface just a plane? Hmm. Okay, let me do some googling. Conical surface. Conical surface. Spherical coordinates. Coordinate curves. Spherical coordinate curves. Well, no, coordinate um coordinate surfaces. Okay, I'm getting an image here. Screenshot, please. Okay, you. Paste. Let me go up here. Boom. We got this. We got this. We didn't get this. Radius. Radius is constant here. We'll move this around. Um, vertical half plane. Hmm. R. R goes out to infinity. Theta is able to change. Yeah. R goes out to infinity. R goes out to infinity. Phi. Okay. R is this direction. This, this. This guy goes like this. This guy goes like this. Okay. At this point he goes up. This point he goes up. Goes up, goes up. Hmm. I think I'll come back to this later. Maybe it'll be made clear at some point to me. Um, in my head. Okay. Well, let me go back to where I was over here. Okay. Oh, we have to go through this. We listened to table 1.1, the definitions of UI and their scale factors. And two common. The coordinate services for symmetrical artists, so services of constant V. Okay. We'll return to that. We'll return to that. One. Coordinates, definitions, scale factors. So by definitions, they mean like writing it in terms of x, like going back and forth, those relationships. So let's just address a cylinder. I assume the cylindrical coordinate starts in the middle of the cylinder. X equal p cos fling p z equals z. C equals z. Hmm. That I don't really care that much, honestly. Why is this p and these are 1, 1? How do you get h again? You get it from doing the partial derivatives and getting the the magnitude. So dx, dr, the del r, del x. No, del. I think so. Del x. Del r, del ui. Well, let's just move on. Finally, we should note that the coordinate r of t of a physical event is a function of time. This can be differentiated with respect to time to give successively its velocity, acceleration, the coordinate bling of a physical event. is a function of time. Yeah, I agree. Yeah, I agree with this as well. If curvilinear coordinates are used, be contributions. There will be contributions from the time variations of both. There will be contributions from the time variations of both the tangent vectors and the curvilinear coordinates themselves. More specifically, we find by dividing by dt that was 1.121. 1.121 dr equal the sum of like the dS's basically. Hmm. dr for dt equal summation of hi ei bling ui equal to ui dt dui dt. It So instead of position, this becomes velocity now. Okay. And earlier they were saying hi works to like bring it back to the units of length. So maybe this is what they meant by this. Because right now it's hmm, never mind, never mind. A direct differentiation then gives bling sum of I, and you differentiate this to get hmm, we end up with two things here. Oh, hmm. It's it's weird to see, but there's like a dot above this E. So this E got differentiated. Okay, dt. Okay. They're treating this as like three guys, so you have to do like some kind of triple product rule. Um, let's do it. Different color. Okay. For the product rule, differentiate one thing and then combine it with the others. So we're differentiating EI to get this EI, and then combine it with the others. UI, HI, yeah, that's dealt with. Next, differentiate the next group and leave this guy alone. So you leave this guy alone and you differentiate the group now. So now when you differentiate the product, differentiate one thing, leave the other thing alone. Yeah. Differentiate one thing, leave the other thing alone. Yeah, I agree with this. Boom. EI differential of a unit vector though. So we have a unit vector. Differential of the unit vector. The gradient of a unit vector sh should be like a tangent, but which tangent? Which way? Okay. In spherical coordinates. Hmm, 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 hmm. Well, let's just keep reading. In spherical coordinates, for example, this reads velocity equal. Okay, well, I can't see. I need to erase some stuff. Velocity equals r. Yeah, r dot er. Yeah, and hi has 1 plus o dot r e theta because h theta is r, And over here, yeah, same thing. Since it is also true that velocity equal differential of like the position vector itself, RER, it is also equal to, we're treating this as a product. So I guess we always have to treat it as a product. Like, even if it's a unit vector, it's still a product with the um, magnitude. Okay, R dot ER plus RER, yeah, RE dot R. We see that E dot R equal, so I assume we're equating these. E dot R equal theta dot E, theta E of theta, plus phi dot sine theta E of phi. So they're saying that the they're saying the ER terms is a pair. If you set this equal to this, you can just cancel these off because yeah. Um yeah, yeah. And you need to divide by R to get this guy by himself. And the R's from here disappear. So the differential of the unit vector in the R direction, in the radial direction, equal the differential of theta. Is this just normal theta? 1.130. Yeah, this is just normal theta. I guess the idea is that theta is a function of x or something. Theta is a function of something. Oh no, theta is a function of time. Yeah, dot means um time. Yeah, everything makes sense. Um, yeah, it makes sense. So the change in E dot R del E del T equal the change in theta with respect to time in the E theta direction plus del phi del T sine theta E in the E phi direction. A result that can also be obtained by a direct differentiation of ER from 1.118. Oh, okay, let's. Are they doing it here? Are they doing it here? I don't think they're doing it here. Let's go back up. 1.118. 1.118. 1.1. Hmm. Uh, ER. Okay, let's go back down. I don't know what they're getting at. I don't see any ERs. Well, I see ERs, but it's kind of wedged into everything. We see that this equal this, a result that can also be obtained by a direct differentiation of ER from here. A direct differentiation of ER. A direct differentiation of ER. Okay, I'm seeing ER over here. I don't see ER anywhere else. Okay. Uh, uh, I'll take a screenshot, I guess. We have some investigating to do here. Okay, paste. Let me go to where it ended up. Okay. Um, zoom out. You select transform. Bring this guy around town. Bring him down here. Make him bugger a little bit. Maybe that's too big. Uh, transform. Deselect. Let's zoom in. Let me check chat. Is anyone here? No one is there. Hallelujah. Praise the Lord. How long have I been streaming? Almost an hour. Okay. Uh, okay. We find by a direct differentiation the result that can also be obtained by a direct differentiation of ER. They're doing it with E theta down here, so let's just look at this. I did all this work to bring this guy down here, but let's just do this. Um, change color because I want to. E dot theta. Wait. Uh, oh my God. I need to bring the entire thing. You delay you, where are you? 1.118. I need to bring this entire thing. Well, I don't really need to. I can just leave it up there and then go towards it. Okay. That's good enough. Okay. So we have uh we have E theta, H theta equal all this stuff here. I can't. Oh, this. Hmm, my color is white. Is it? Yeah, it's white. Oh my God. Color. I almost pressed X. That would have been a tragedy. Color. Not white. Okay, you can go now. We have E theta times H theta equal all the shenanigans. We can factor out R. Just have R to the side here. And then boom, get out, get out, get out. Okay. Um, um, I'm looking back and forth between these guys there. Uh, uh, differentiate with respect to time. Okay. Theta multiplied by all this plus phi multiplied by all of this. 1, 2, 3. Hmm. Where did the z component go? That's what I'm wondering. Oh, the z component is in here. So maybe you can like factorize it after the fact. Maybe. Maybe. Uh, hmm. Okay. Let's. H hit as R, right? I think so. H theta is R. Let me check. H theta is R, yeah. H theta is R. So we can just cross off this R one time and cross off this H theta. So we already have E theta equal those guys in there. Um, so I guess let's bite the bullet. Let's differentiate. So cos theta cos phi EX. I really don't want to do this. Okay, differential of cos theta is minus sine theta, right? Minus sine theta. And then you have to multiply it by cos phi because product rule. And then you add that to minus cos phi sine theta. Minus the minus no, wrong. You add that to minus sine phi sine theta because sine doesn't change. So that's this. But there's also EX. Oh my god. Oh my god. But I don't see any over here. I don't see any EX dot. So maybe the EX dots cancel out. Which sigh. I have to check that as well. Uh, let's do it, I guess. Okay. Um, EX dot multiply by the normal stuff. Cos theta, cos phi. Now you add the differential of this, which is this here, which is this. You multiply that by EX, yeah, voila. I think that's it. Am I missing a step? I differentiated this entire thing to get dot EX multiplied by this guy. And then I proceeded to differentiate this guy, which is this guy. Then I had to multiply by EX. Cos theta, cos phi. Yeah, I think I have it. Yeah, maybe. And cos. I'm still a little confused. Where did this guy go? Where did the E dot X go from here? I don't see any. We move. Maybe it'll be made clear. Next up we have, let me change color. Changing color is not the best. I'll do it here. I'll do it over here. Um, we have EY dot multiplied by cos theta sine phi plus EY multiplied by the differential of those guys, which is minus cos theta sine, no, no, minus sine theta sine phi, uh, minus sine theta sine phi. We're done with that, surely. So now we just add this differentiated, which is cos theta cos phi. Am I missing something? I feel like I'm missing something. I, it, hmm. No, I think this is correct. Let's just do easy dot. Oh, easy is just easy is easy. We have easy sine theta, and then we add that to cos theta easy, cos theta easy. But all this needs to be negative because for some reason over here there's a negative sign. I can't remember why. Okay, let's see how this relates to what they got over here. Let me erase this in case there's a secret dot. There's no secret dot. Theta dot uh uh oh, hmm uh where did they get theta dot? I don't see any thetas in there. Maybe it's something where it's like cos the differential of cos AB, well ax plus b is a, well, a minus a sine ax plus b. Like maybe you're supposed to treat theta as like a guy that can come out of like a constant. No, that doesn't make sense, does it? Do you treat theta as a constant? Theta is a variable though. Hmm. Hmm. Okay. Well, let's move on to this guy because he's slightly simpler. Like maybe we can get some refuge here. So we crossed off the r sine thetas because we can, because h of phi is r sine theta. So you can get rid of that on both sides. You remain with sine phi ex cos phi ey playing equal. Okay. E dot. Hmm. Okay. Let me differentiate this and examine them very, very closely. Like I think that will help. So E dot U. So how do we treat that? Theta equal, let's just say AT. Is this a good enough interpretation? Theta equal AT. I'm spending too much time here. Am I? Like, well, what's next? Okay, it's just more shenanigans. I guess it's not wasted time if you're figuring stuff out, maybe. Okay, theta equals something t. Theta is a function of time. So in doing that, oh, I understand. I understand. I understand. This thing, I understand this thing now. Let me try and, I understand the theory. Let me understand the specifics. Like, let me remember what it actually looks like. Hmm. Hmm. Okay, let's just differentiate. D theta dt. Is this is this fruitful? equal A. Yeah, 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 yeah. Yeah. D theta dt equal A. So this just means that theta dot equal A. So oh my God. AT blah 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 blah. So the ddt of cos theta, let's go back to purple land, equal, let's get the minus and the sign out of the way. Let's put back theta. A would just be, it's just the differential. You're just differentiating and putting it in front. Like it just looks like a formula, but it's the solution. It looks like a general solution, but it is the actual solution, which is a general solution because we're just dealing with the equations, but that is besides the point. I really like to put my brackets. Bracket addict. I should add that to my like list of things that I have. I'm a bracket addict. What type of physics do you like? Um, I I like all of it basically. Um, which part of physics do I not like? And you can answer the question too. What type of physics do you not like? Uh, hmm. What type of physics do I not like? I know which part of physics is confusing, but that doesn't mean I don't like it. Like whenever you get to circular motion and stuff like that, like the oscillating stuff, that that gets confusing, but I still like it. If I had to choose a job in physics, I still can't choose because I like the whole thing. If you're here, you answer as well. You answer as well. Um, but for me though, I think I'm going towards astrophysics, and the only reason is I won't run out of stuff there. Yeah, you too. Good luck, brother. Cause Milano, cause Milano. Okay, let's continue. Um, um, I already did some work here. Okay, cos theta ex, cos. Okay, I think everything remains the same. I just need to add in like the theta dots in front of these guys. Theta dot, theta dot, theta dot. Wait, not necessarily. These guys don't need theta dots because in this case I differentiated the EX guys and the EY guys. So only these guys need theta dots. Right? But this isn't theta, this is phi. Phi dot. Phi dot. Is there any thetas in there? No, we cancel out the thetas when we got rid of HI. Okay. Um, Phi dot. Oh yeah, good, good. I was worried I saw four terms there, but no, it's just two equal signs over here. Phi dot minus cos phi ex. That's what I got here, yeah. Minus sign. Minus cos. Yeah, I got the minus, yeah. Oh, there's a minus here, but I'm blocking it with my purple stuff. Minus sine theta ey. Well, where did these guys go? Where did these guys go? Are we not interested in those guys? Why are we not interested in these guys? I'll figure that out later. Um, different color. He took out the minus sign, so it's out here now. We end up with sine theta ER plus cos theta E theta. Sine theta. They switch from phi to theta, and they switch from EX EY to ER E theta. Why? How come? How come? Is there a relationship between EX and the ERs? There is over here, yeah. Hmm. It has nothing to do with this, because that's already dealt with. Cos phi EX, cos phi EX, sine theta ER. XYZ isn't just placeholders, they're actually XYZ, because we got these equations from relating Cartesian to spherical. Sine theta ER, cos phi EX. Oh, maybe, maybe. I was thinking maybe it has something to do with this guys, the guys that I was confused. Where did they go? But these guys are thetas. Well, these guys are phis, and these guys are thetas. So that is kind of weird. Is it a typo? It's most likely not a typo. Surely they have this correct. I'll figure it out at some point. Um, let's just look at the other stuff. Um, what's the time? We're almost hour and a half, so I'll stop soon. I've been slowly going on for more and more. Like it started off with 90 minutes, then 100, and last stream was like, I forget. I forget. What's this? 11 other OCC systems and free videos are here. Let me draw a little line. Oh, some lines. Oh, okay. Elliptic, cylindrical. When I think elliptic, I think oval. Maybe that is wrong. When I think elliptic, I think like I think that's the name for the line the stars make over in a year. The part the stars take, if you look at the sky over a year, like it changes slightly because of a bunch of reasons. Maybe it's for the sun. It doesn't matter. It doesn't matter. I still think elliptic is about ovals. Like ellipticity is that a word? Eccentricity and also ellipticity, something like that. So oval plus cylinder. So some kind of coordinate system like this. Parabolic cylindrical. We have a cylinder. Somehow parabola is inside of this. Bipolar cylindrical. So polar is circle. Maybe bipolar is like double circle somehow. Somehow. But it's also cylindrical. Prolate. I have no idea what prolate means. Oblate. Oblong. I don't know what prolate means. Parabolic, yeah. Parabolic coordinate system. I assume like each point, like one of the guys points in the direction of parabola, and the other guys make up the plane perpendicular to that direction, I assume. They have the definitions of XYZ here, but I don't I don't believe in my ability to grasp. Wow. I just noticed how insane these ones are. I don't believe in my ability yet to grasp the directions of these things by looking at, oh, sine H, sine V, sine. It's insane. Um, yap, yap, yap. Yap, 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 yap. Toroid. I don't know what that means. Bispherical. It's like two spheres, somehow. Confocal ellipsoidal. Why not elliptic? They use elliptic up here. Ellipsoidal. What does oidal mean? Spheroidal. Cylindrical. Why not cylindroidal? Spheroidal, ellipsoidal. Either way, I'm thinking like a 3D oval. Ellipsoidal. Spheroid. Confocal. I know I know roughly what focal means. Condo? Cone? Cone focal? Cone? You combine a cone and also a ellipsoid and a focal point, focal lens, focus. Like focus is just like the middle of stuff, basically. Like for an oval, they have two focuses, two foci. Confocal. If it was bifocal, it would, I don't know. Conical, just a cone. I wonder if, no. I was thinking like maybe these don't actually describe all points in space. Like they only cover like some points in space. But I think by definition of a coordinate system, it has to cover every point in space. And also a second argument is you can just rotate. You can just rotate the coordinate system if that was even the case. Confocal parabolic, a parabola, whatever this confocal thing again, I don't know. Maybe there's like 2 points in the parabola that you go up and down. Maybe you go something like this, where like one of the parameters like rotates the second guy, and and the intersection of the two parabolas is the point. That that's complicated, but at the same time, these equations are really complicated. At least it looks that way. Um, yap. Problems. Let me just skim these problems. I'm not gonna do them. I might at some point. Obtain the unit tangent vectors ER cylindrical in the system so that they are orthogonal. Obtain the scale factors. Okay, I can't lie. Like these sound like interesting questions. Like this whole H thing. Like I'm saying like a lot. Do I say like a lot? I don't think so. Um, this whole H thing, where you can define a coordinate system from H's and the DS's and stuff. It's surprisingly simple. I say that after I see this, but still, it's still, there's order to it, and that's good. So I feel like these questions, I would like to do these questions. But are they referencing other books to do the questions? Found in plots of some of this, so you get some help in the other textbooks. There's some parametric shenanigans. Blah, blah, Okay. Cylindrical. Yeah, like these look like I would have. I feel insane saying this. I might find joy doing these questions, bro. Okay. I think it's not enough. I think I'll finish now. I did some good progress, in my opinion. The only opinion that matters. Next we have like a bunch. We have a really long chapter next. Oh, the next chapter ends. Next chapter ends chapter one, I think. What? And then we move on to matrices. So next stream I should finish chapter one and then matrices. I hated matrices at first because I still do, but it's so there's so much work in matrices. There's so much jumping around. There's so much like it makes no sense. Matrix multiplication. Wow. It's like you're really reaching to make sense of this. And I have realized that the further you go into maths, well, at least from the textbooks I see, you're never going to get rid of matrices. It'll always be there. So I have to learn to love it, I guess. That's the end of stream. Cause Milano. Farewell, cha cha ta ta, cheerio, chip chip, chip 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 chip.